Vidal from the Autonomous University and IFIMAC. And for me, it's a pleasure and a privilege to introduce Professor Pendry, the speaker of this summer school, although he doesn't need any introduction, but nevertheless, I have to say something about it. So, Professor Pendry has made very important and seminal contributions in different fields within physics, from condensed matter physics to optics, something that is not very common nowadays. At the beginning of his career, he focused on analyzing the electronic properties of surfaces, and in particular, he developed theories that enable the practical use of experimental techniques as low energy electron diffraction or angle resolved photoemission spectroscopy to take use of these techniques. And he also invented the inverse photoemission technique. And in the 90s, he moved completely his research to a new emerging field that is nowadays called nanophotonics, in which he made also important contributions to photonic crystals and plasmonics, even when plasmonics, the name plasmonic was not used, and more importantly on metamaterials, of course. I mean, not many scientists can say that they have created or built up a new area of research, and John Pendry is among them. So, of course, he has received many awards and recognitions. So he's a fellow of the Royal Society since 1984, so 35 years ago. And more recently, he has received the Dirac Medal in '96, the Royal Medal in 2006, the UNESCO Niels Bohr Gold Medal in 2009, the Isaac Newton Medal in 2013, and the Cabrera Prize in Nanoscience in 2014. So, John, thank you very much for coming.
Thank you, Francisco, and good morning. It's a pleasure to be here, this beautiful location. I've not been here before, it's a privilege. I want to talk to you about work we've been doing over the past decade, I think, on controlling nanolight. And there are two themes to what I have to say today. One is the supreme importance of structure of the material that you're using to control nanolight. And the second is the design technique we use, which is transformation optics. To begin with talking about the importance of structure, I like to use this analogy, how you can change the properties of silver simply by altering its structure. So you're familiar with the fact that a flat surface of silver is highly reflecting. It's about 95%, one of the most reflecting things you can have. But if you grind it up into nanoparticles, then it's one of the blackest things you can have. And the whole noble metal sequence, silver, gold, copper, and so on, they show this property. They're used as absorbers in bolometers. You're probably familiar with it in the old-fashioned black and white photographic negative. The black is due to silver nanoparticles. So a very dramatic transformation simply by altering the structure. Now, the other theme is transformation optics. And the idea behind this is to bring Snell's law up to date, but at the same time with a technique that preserves the accuracy of Maxwell's equations. Snell's law is still deployed, of course, and the reason for that is it gives us this very intuitive feel of how light behaves and how its behavior might change if we alter some of the parameters of the system. We can see in our mind's eye how light can move through the picture of rays. But Maxwell's equations work with another picture, which is fields, and Faraday thought about electricity and magnetism in terms of field lines, and that's the way I think about light, in terms of the electric and magnetic field lines. And we realized some time ago that you could manipulate these field lines by, in effect, changing the geometry. So imagine that you could somehow alter the geometry of space, that you could bend space. You need a few black holes, I suppose, but you could bend space. And if you did, then the space as it is distorted would carry the field lines with it, both electric and magnetic. So by suitably distorting the space, you could alter the trajectory of the field lines. And then you recognize that if you look at Maxwell's equations and write them in a geometry which is distorted, then you discover that the effect of distorting the geometry is just the same as changing the values of epsilon and mu according to this algebraic formula here, which is expressed in terms of the first derivative of this distortion, expressed as a coordinate transformation. So we don't need to distort space, we just need to put in place the appropriate values of epsilon and mu, and then providing those can be realized, we can manipulate the fields and therefore the light as we wish. There's a simpler way of looking at that, the effect of that distortion in terms of geometry rather than algebra. Different people's minds work differently. Mathematicians would prefer the algebraic approach, but I prefer the geometric approach. So imagine that you squash space this way. So I have a trajectory here. And by the way, this rule of carrying the field lines also applies to all conserved quantities. So the pointing vector also is carried with these distortions of space. And you can think of the pointing vector as a more precise formulation of the rays of Snell's law. I'm going to take this instance of a pointing vector, a ray of light traveling in this direction, and I'm going to compress this middle region of space here. And then the ray will go along here, the pointing vector will go on here, and I ask what values of epsilon mu will send it there. And the answer is that if I compress this way, then perpendicular to the compression, I increase epsilon mu by the inverse of the compression ratio. And along the direction of compression, I decrease epsilon mu. So increase, decrease. And by applying that rule along all three axes, you could make any shape you want if you add a little bit of a twist. And the twist doesn't do anything other than reorient the tensor. So that's transformation optics at its simplest. We're going to be thinking very much in terms of surfaces of metals, because they give us access to excitations on a scale which is the nanoscale. And these excitations are the surface plasmons. They're often, the electrons in a metal are often described as an electron C. And just like the C, the electron C has waves up on its surface, charge density waves, and these are surface plasmons. They've been well known for many years. Rufus Ritchie was one of the earliest, in fact is credited with the invention of the concept of the surface plasmon, and they disperse first of all linearly at low wave vector following the light line, and then as they become more electrostatic in nature, as they deviate from the light line, they go asymptotically to what's called the surface plasmon frequency, which is the bulk plasma divided by √2. Many will be familiar with that. And they're often modeled by what's called a Drude form of the dielectric function, which is negative when omega is below the surface plasma frequency and positive, below the bulk plasma frequency and positive above. It also includes loss if you want to make this gamma finite here, which makes epsilon imaginary. And I shall use this model quite frequently in what I have to say. I think it's true to say that people began to realize how extraordinary our surface plasmons were with this experiment which was performed many years ago by a man called Fleischmann. Anybody remember Fleischmann? What did he do? Yes, what else did he do? Cold fusion. Anybody remember cold fusion? But this is the thing he really did, which was surface enhanced Raman scattering. and he was made an FRS for that until he got into serious trouble with other things. So many of you will know what the Raman effect is. You shine some light in at a given frequency. It loses a bit of energy to a molecule, the vibrational modes of a molecule, and it goes off with slightly less energy because the phonon has so much less energy than the photon. It's a rather weak process with a very few exceptions. So normally if you put a layer of molecules on a metal surface and tried to see the Raman signal, for most molecules it would not be detectable. But Fleischmann did that experiment and he saw a huge signal. And it turned out that that huge signal was somehow connected with the fact that the metal surface wasn't a flat one, it was silver, but it was rough silver. And there was intense debate about what this surface enhancement was due to. The chemist said it's a chemistry effect, the physicist said it's all to do with electromagnetism. We were right, okay. So when Francisco worked with me in the 90s, we were very interested in this problem, and some of his calculations contributed to the resolution of this issue. Of course, it turns out, and this will be another theme of what I speak about today, that if you have some sort of singularity in the structure, and the one we considered, it happens for any singularity, as I'll show you, but the one we considered was two touching cylinders. And in that case, the cylinders actually act as a magnet for the radiation and concentrate it here. And the Raman signal is proportional to the fourth power of the enhancement. So you only need a factor of 100 or so, and you're into very, very serious enhancements of the Raman signal of the order of 1,000,000. And that was really created a huge amount of interest from the optics community in surface plasmons. There'd previously been a very great deal of interest from the electron microscope community, who can use high-energy electrons to excite the surface plasmon, and that indeed is how they were discovered experimentally. Singularities are important. They enhance spectroscopic sensitivity, possibly to single molecule sensitivity, as in the SIRS enhanced Raman experiment. And this happens because they can create very intense fields locally using modest power. And this gives access to nonlinearity at modest power, because you can create locally very, very high density of energy. And using nonlinearity, you can use light to switch light, or get into more exciting things such as do phase conjugation and time reversal experiments. Also, there are applications in the field of medicine. Naomi Hallis talks about sensitizing gold nanoparticles so that when they are illuminated with radiation of a certain frequency, they release drugs which are trapped on their surfaces. Gold nanoparticles can migrate easily to cancers, unlike other organs in the body, because the cancer grows with very open structure. And so the gold particles easily penetrate the cancer, and preferentially. And so it's seen to be a good way of treating cancer. The singularities are, you can have many varieties of singularities, but they all seem to have a common origin of a singular transformation, as I'll show you. Let's take the simplest example, which I've introduced already, which is the case of two touching cylinders. And I'm going to transform that to another structure. And by the way, I mentioned that we're going to use the technique of transformation optics. Here's the transformation which we're going to use. I'll discuss it in a moment. But the theory of transformation optics is an exact one. So if you do what I described with the algebra or the geometry, then you get a system which does precisely what the math says it should. But there are various hierarchies of approximation. One is to confine yourself to two-dimensional systems, and then you can use conformal transformations. And in conformal transformations, a great simplification comes. So remember, I compress this way, you increase and decrease. And now if you make it conformal by compressing an equal amount that way, you increase and decrease. So you're back to where you started. So all the in-plane properties of a conformal transformation remain unchanged. So silver goes to silver. Only the outer plane properties matter, and they only affect if the wave is propagating in plane and the electric fields are in plane. Only the magnetic field sticks out, and that is not invariant. But if the system is very, very sub-wavelength, then the excitation tends to be purely electrostatic. So on the nanoscale, electricity and magnetism separate. They're two different excitations. The electricity doesn't create much magnetism, vice versa. So for very, very small systems, for very short wavelengths, we can actually ignore the outer plane magnetic fields, and silver goes to silver. Let's have a look at this transformation. This transformation is an inversion. You can express it in terms of complex numbers. Z prime is 1 upon z. And its effect is to take points at the origin to infinity and points at infinity to the origin. And all circles in between are converted either to other circles or to straight lines. And in this instance, if you invert about a point on the circle, the touching point, you get two straight lines. So this transforms to a waveguide that is uniform in this direction and has the same in-plane epsilon as does silver. And so by making a singular transformation, a singularity at the origin, you can remove this singularity and show that as far as the spectrum is concerned, this touching cylinder system maps onto this system of a translation invariant waveguide. Now, I was talking about this in Paris some years ago, and somebody in the audience says, but what have you done? This can't be right, because this system here has a whole lot more symmetry than this guy. This guy just has a couple of mirror planes, whereas this system here also has a couple of mirror planes, but importantly, it has translational symmetry. And that means that the states of this system can be classified in terms of block waves. Now that's, in condensed matter physics, the Bloch theorem and translational symmetry are hugely important. Electronic structure calculations are predicated on the assumption that you can expand a system in a system of Bloch waves. If you move away from ordered systems and go to disordered systems, our understanding of disordered systems is incomplete, and you can only work to understand them in terms of approximations. So symmetry is very, very important, and in this instance it enables you to classify the excitations of this system in terms of the Bloch waves. So you can calculate in this system, and then you have the spectrum in this system, which happens to be continuous, and then you can map by a coordinate transformation the solutions in this frame map to the solutions here. And of course, because they're distorted by this singular coordinate transformation, they look crazily different at this point, but nevertheless, hidden within them is the symmetry of the Bloch theorem. So here's another way of expressing that. The other thing which we need to know is how are you going to excite this system. So typically you will excite this system here of cylinders by an incident plane wave, which produces a uniform electric field. Now the important thing is that uniform electric field, and if I say, well, I don't have to make the electric field like that, the other way I could do it, which was completely equivalent, would be to have two very large charges a very large distance away from here. And that would create a uniform electric field at this very small object. And then when I invert about this point, charges very far from the origin go to charges very close to the origin. And so illuminating this system with a uniform plane wave, a uniform electric field, is equivalent to exciting this system with a dipole, because a dipole is just two large charges very, very close together. So uniform fields map to dipoles if you invert about this central point here, and that enables us to calculate the spectrum of this cylinder. And Antonio labored away on this problem some time ago. Okay. Now that's not the only transformation you can apply. If we start with this waveguide and call that a mother structure, of course that's where the symmetry is, that's the easiest to understand, you can calculate it analytically. And then you can apply all sorts of transformations which screw up the geometry in a whole mass of different ways. And we call these transformed structures the daughter structures. So a single mother structure will pass on the genes, the spectrum of that mother structure to the daughters. Not only that, but the symmetry as well, and also the analytic solutions. And so in this way we've been able to have detailed understanding of things like van der Waals forces and near field heat transfer, as well as spectroscopy. Here's what I call the zoo, which is put together by Yu Liu, who's now a prof in Singapore. Where are we? This one you've seen of a waveguide, but now if I put periodic dipoles in here, I can think of a transformation, or Yu Liu can think of a transformation which transforms this into two cylinders which aren't touching. And in the limit that this periodicity goes to infinity, you can imagine these cylinders coming together to the touching limit. Another structure is to put a dipole outside the inversion of this structure, which is a slab of silver embedded in a dielectric, and inverting about the dipole gives you this crescent structure here, and this is the singular point here. And that's a structure we've looked at. I like this one very much. So we have a periodic structure here, which is translationally invariant in this direction, but periodic in this direction. So silver dielectric, silver dielectric, silver dielectric. And if you make a transformation e to the z, rather, then this length transforms into log of a radius. Log of a radius. So if you start in the silver, you go off to minus infinity at the origin, maps to the origin, and plus infinity maps to plus infinity. And if you go along the y direction, that maps to an angle here, then you go silver dielectric, and round in angle, silver dielectric, silver dielectric. So this periodic structure here of waveguides maps into a knife edge. And then there's all sorts of stuff you can do about things embedded one with another. You choose your transformation, you can make lots of different things. And here's what happens in the singular crescent structure when you irradiate it with a plane wave. So in the waveguide, let's start with the waveguide, I suppose. In the waveguide, the radiation corresponds to switching on a dipole here at the origin, and that dipole will excite surface plasmons in the waveguide, and the surface plasmons will propagate away to infinity. They'll never get there, but they propagate with a constant velocity to infinity. On the other hand, in the transformed structure, these waves are excited not at this point here, which corresponds to the furthest extremes of the two touching cylinders, which acts like an antenna, and then the light is harvested and propagates towards this singular point here. But just as this excitation never gets to plus infinity, this never gets to the origin. It goes slower and slower, and the analogy one could make is of cars on a motorway, which as they go slower, they come closer together, so the energy density gets higher, and that's the point of this figure here. So what I'm plotting here is the electric field as a ratio to the incident field, a unit incident field, as a function of angle here. As we go around from 0 to 180 degrees, I start at 174 degrees and finish at 180 degrees. And you see that two things happen. This compression through the coordinate transformation shortens the wavelength, but at the same time, it increases the energy density. And if there were no losses in the system, the energy would climb to infinity at this singularity here. Is this your figure? Yeah, I think it is. Yes, thank you. Thank you very much. But the singularity is not achieved because the losses in the system act upon this concentrated wave, which the more slowly it goes, the more vulnerable it is to loss. And eventually the loss takes over and the whole amplification process collapses. But before it does, you're enhancing the field by a factor of 1,000. Now that turns out to be a bit idealistic because you couldn't make this ideal structure and there are other things intervene, but you can certainly get enhancement factors of the order of 100, and that gives rise to these very, very huge concentrations. These, by the way, were realistic numbers taken from Johnson and Christie for the silver. The only unrealistic part of them is that it's actually important to include what's called non-locality, but I shan't discuss that further today, other than to say that it often spoils the party for plasmonics. So here's in printed words what I've just said verbally. The waves propagate to the origin, are compressed, and you get the high intensity there. Losses stop the system going to infinite density, and all these modes can be classified in terms of block waves. So the message is a common origin of enhancements is a singularity at a singular finite point which a transformation can map to infinity. And there are lots of such transformations. So here's another way of looking at it. This is, I think I mentioned that you could calculate the spectrum for two cylinders which are separated, and as you bring them closer together, what you see is here is the absorption crest section as a function of frequency. This is a surface plasma frequency. Isolated cylinders have a single excitation at the surface plasma frequency, and as the two cylinders come together, all the different harmonics hybridize and cease to be degenerate, and they spread out, and eventually when the cylinders touch, these this diverse spectrum fuses into a continuum. Well, something else you can do is to say, we thought about how light interacts with the system. How does an electron interact with the system? And this has been a problem which has been studied for many years, but without realizing that there's an underlying simplification that you can make. Pedro Echenique, who many Spanish people here will know of Pedro Echenique. What you may not know is he did his PhD with me, and he did it on electron energy loss. So this is harking back to some of Pedro's work, brought up to date by transformation optics. The problem is this, that you have two touching, let's say, cylinders. You can think of spheres as well, but cylinders are simpler. And you have an electron going by. Now, typically in a microscope, electrons have 10, 20, 30 keV of energy. And if they lose the odd EV or so to a plasmon, they don't care, they just charge on regardless. So essentially this trajectory is determined by the energy of the electron, and using the imaging capability of the microscope, you can position this beam wherever you want. You can send it here, 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 or right through them, wherever. It's a very, very nice technique. And so the challenge is to calculate how much energy is lost by that electron as it passes by this system. If I make an inversion of this system, then I can go to the system we thought of before, or the waveguide, and in this system, the modes that you're exciting can be calculated analytically. They're just blockways in the system here. However, it really messes up the electron trajectory, because the electron starts at infinity, which maps the origin, and it finishes in the infinity, which is also the origin here. And in between, it goes round in a circle, starting off slowly and then zipping round like that. You wouldn't like to calculate the electrostatic field of that electron. Fortunately, you don't have to, because the electrostatic field you calculate in this frame and then transfer here. So you know the electrostatic field here from the mapping, and then you know the modes here because they're simple in this frame, and then you just ask, how does this electrostatic field excite these modes? And the answer is here, calculated by you know, and here's the energy loss as a function of energy, and here's the surface plasma frequency, that's the bulk plasma frequency, and the electron has far fewer selection rules than the photon, so you see all the modes, symmetric and antisymmetric modes, excited here. More visually interesting is this little video by Matthias Kraft, and he's got this crescent-like structure here. He's actually got, the crescent isn't singular because this is very thin here at the near touching point, but they don't quite touch. And what you're going to see is an electron coming by, kaboom, and the plasmons, it's like hitting a bell with a hammer. You'll see. So here comes the electron, crash. It rings like a bell. And notice how the intensity gets large when the plasmon slows down and goes by this gap here. Okay. Right. So far I've talked about finite systems, at least finite in 2 dimensions. But another way to excite plasmons, surface plasmons, is to make a grating or a metasurface if it gets a bit more complicated than an ordinary grating. And in fact, you can generate almost any grating, shape of grating with a conformal transformation. I start with the flat surface, the waveguide, which is a mother of all structures. And then that, through a log exponential transformation, can be transformed into 2 cylinders here with silver in between, if this is silver. And that's the origin for this transformation here. And then I can make something like an angular Fourier expansion, a power series in the complex number Z, and then I can transform this surface here to some complicated shape which is described by this expansion here. And then I can go back through the log transformation, and this angle becomes this coordinate here, which repeats this angular structure, but now repeats it in the grating space. And we're going to explore that through perhaps the simplest transformation that you could make. So here we go from the grating to the embedded cylinder, and then I make an inversion, not about this point, but about this point here. So the symmetry of this is hidden. It's not destroyed, it's hidden. And here we have a system of 2 embedded cylinders. And then we take the log, and that gives a grating of a finite thickness, but one surface is wobbly here. Now, a little bit of a complication here. Now, I have hidden a few truths from you. And what I've said is that these daughter structures inherit the mother structure, and that's true if you go this way. But there's a little wrinkle, and that is that in this system here, the wave function has to be continuous around this ring. Now that's not true in this structure here, because I haven't drawn, well, maybe it's obvious here. It has to be continuous around this ring, and that means essentially it's got to be continuous along this structure here. And what this means is, in terms of the block wave, is that the block wave vector has to be 0, and then the wave function is the same at every period of the cell. But block waves come in a greater variety than that. You can have a non-zero block wave, and in that case you run into a problem, because that's not a set of solutions present in here unless you introduce a cut into the structure. So it's only at the origin of the Brillouin zone that you inherit this spectrum here. Elsewhere you can use the computational technique, but you have to take account of the branch cut, and that means the spectrum isn't quite the same. Just to give you an idea of the shape of these transformations, if you have a very weak transformation, then straight lines go to these slightly wobbly gratings here, and as you change the parameters of the grating, you can make the grating have a more and more emphasized straight, and eventually when the parameters go beyond a certain point, the grating breaks up into a series of blobs. So quite a rich transformation in terms of generating a surface structure. That's what some of the weaker transformations look like in terms of the modulation of the surface. And this parameter W, which pops into this equation here, the bigger W is, the greater the modulation of the grating. So I'll show you a few results for that. Here is the dispersion of the grating in the quasi-static approximation, in which I've neglected retardation, ignored the magnetic fields, and this is relevant for a very short period grating. And the structure is very interesting, at least to me. So here's the first Brillouin zone, here's the second Brillouin zone, and at the origin here, the spectrum is exactly the same as a flat surface. So all the modes are degenerate at the surface plasma frequency, and that is required by the hidden symmetry of the grating. All the modes are degenerate at the origin here. But that is surprising, because this is quite a strongly modulated grating. It's a W of 2.5, and 2.5 is like here, so it's quite a wobbly grating. But nevertheless, despite that, at the origin, it obeys this iron rule of symmetry, that it doesn't change the spectrum at all, even though you've modulated the grating. Move away from there, the branch cut swings into action, and you get this huge splitting here of several EV. If I have time, I'll natter on a bit about that and its consequences for the surface tension of that grating. You can do the full transformation optics. It's a little bit more complicated, much more algebra, and when you do that, and these are some calculations which Paloma or Roy Hodobro did, she'll be back in San Sebastian in January or February, and compared with the COMSOL calculation, you see, of course, it's an exact theory, so not surprising there's exact agreement. So if you refer back to that structure here, the light line will come up somewhere there, and so it's going to smash into this structure of this first band here. These higher bands aren't affected because they're really to be translated along here and along here, so it's just an accident at the origin. So this band will be very much distorted by the lifeline, and you see that it's eaten up by the lifeline and disappears into a surface plasmon polariton and a higher order mode. And then these guys here are unaffected by the light line. Yeah, I'm going to skip that. I don't have. So I want to start on another theme now, and that is, well, maybe I have time to talk about that. Yes, okay, which I will do. One thing that these dispersion relations tell you about is what is the change in the surface energy of these structures. Now, any system with excitations in it, the excitations always have a 0-point energy. And if you add up that 0-point energy for the surface modes, that is the surface energy, if you like, the surface tension of that system. So if you start off with a flat surface, then all the modes are degenerate, an electrostatic approximation at the surface plasma frequency. But if you then introduce a grating, you split these modes, you push some up and some down. Now, in electron physics, when you introduce two hydrogen atoms together to make a hydrogen molecule, you also get a splitting of the S levels of the hydrogen atom, and they go up and down approximately by an equal amount. And that's because if you look at the Schrödinger equation, the energy appears linearly there. So when you have a matrix that splits them, the energy goes up by delta and down by delta. So the net change in energy is 0 if you occupy both levels, and then the hydrogen molecule will fall apart. But with electrons, you've got the option of putting the electron at a low level, and that bonds. In contrast, in Maxwell's equations, if you solve for the electric field, the frequency, which is the energy, appears as omega squared. And this is an important point. So when you do the matrix diagonalization, omega squared goes up by delta for the higher mode and down by delta for the lower mode. Well, what I'm plotting here is not omega squared, it's the square root of omega squared, right? So although omega squared goes up and down by equal amounts, when you take the square root, the higher one goes up by less than this one goes down. And that's a general truth of hybridization of optical levels, that the hybridization generally produces a decrease in the 0-point energy, because this mode goes down more than, and it's quite a lot. So this goes up by I don't know, 3, 4, 5, 6, by 2 eV, and this goes down by 3 or 4 eV. So there's an eV's worth in this per mode, and then you've got to sum over all the modes, of course. So the possibility is that metal surfaces like to make gratings, at least as far as this van der Waals energy is concerned. Of course, there are other reasons why they may not want to do, because it involves some elastic distortion of the surface, and if the elastic forces are too great, then it won't happen. Nevertheless, it is true that nearly all metal surfaces are unstable, which I know from my work in surface science. Here is an example. So this is clean gold 100 surface looked at by STM. And the gold surface reconstructs a very complicated pattern which has a periodicity of 28 periods in this direction and 5 periods in this direction. And you can just see the gold atoms here. Can you see them at the back there? And that's fairly typical. I think nearly all the gold surfaces do it. Tungsten does it, silver does it, copper does it. And so what's going on? And it's not just, that's not just the surfaces which show instability. If you're interested in the theory of superconductivity, high TC superconductivity involves layered materials, and there's a very sort of strong two-dimensional element to that electronic structure. And they too show instabilities, and there are theories of high TC. There isn't a full theory of high TC, but some people think that it has to do with the incidence of something called stripes, which is a periodic reconstruction of these layers, which is an instability of the system. Another example of that would be if you take the very fashionable subject of the dichalcogenides, molybdenum disulfide and so on, which the graphene crowd are moving on to now. If you intercalate those with alkali metals, the alkali metals just love to go in two-dimensional layers between the dichalcogenide layers, and they too have instabilities, and those have been looked at for more than half a century with electron microscopy. So this instability is something of a mystery. People have not been able to, by the way, gold is a very difficult metal to do electronic structure calculations for, structural calculations. This structure here is a huge unit cell and a very great challenge, which as far as I'm aware hasn't been met. So this is something of a puzzle, and I'm throwing into the pot, do these plasmonic-like instabilities contribute to, you do sort of back of the envelope calculations and the energy works out perhaps as much as 0.2 an EV per atom, which is a lot for a reconstruction. I'm not saying that it is the driving force, but something that should be thought about. So having said that, I'll move on to what I was going to say before. And here's some work looking at the reflectivity of a grating on silver. This is the shape of the silver grating, and again, it's an exact theory, so we can compare with COMSOL. It's a bit pointless really, because it always agrees. And this is the spectrum of a silver grating. Now, the reason I show this is that I want to make the point that non-singular gratings are colored. So if you look at this grating, you would see the colors represented by these peaks in the reflectivity spectrum. And it's sort of obvious really, because if you take a CD and you put it in a light, then you see the flashes of the diffraction color. So I'm just driving that point home. Non-singular gratings are colored, okay? Now I want to talk about singular gratings, and I want to talk about it in the context of dimensionality. This interested me because we have a bunch of string theorists in our department, very bright people working on geometry in 12 dimensions, and maybe you talk to some of these guys, and after a while you say, well, what's with these 12 dimensions? I know about 3, and there's another one called time, which it makes 4. But where are the other 8 dimensions, or whatever you want? And they go, oh, no problem. They're all rolled up. You can't see them. And I never knew what that meant. Do you know what compacted means, rolled up? But it turns out that there is an example in plasmonics through singular surfaces that is an instance of a hidden dimension. So here's a second hidden. You had hidden symmetries. These are hidden dimensions. Let me tell you how they go about. So ordinary non-singular gratings are characterized by 2 wave vectors. They're 2-dimensional. The frequencies are specified by the angle of incidence. So if you look at a certain angle, you see a certain frequency, that's a certain color. All right, so they're colored. But singular surfaces are different. They're characterized by 3 block wave vectors, and one of which corresponds to a rolled up dimension, and it's rolled up into the singularity. I'll show you how in a minute. And this compacted wave vector is not subject to any conservation rules, and that enables absorption to take place at any frequency at any angle of incidence. So singular surfaces are black. And I would make the point that that second slide I showed you of the black silver surfaces, the silver is probably black because of singularities. So you're actually looking at compacted dimensions. Tell that to the string theorists, and I have. So here's how to do it. We start with this system here, which is a stack of silver slabs. So you have 1, 2, and then into the board is a third dimension. This is a thoroughly three-dimensional system. And I'm going to compress this dimension into a singularity, or actually two singularities. And so I'm going to hide this dimension. But its effects will be there because the solutions in this frame are block wave vectors, and that will dictate what the spectrum of the ultimate structure looks like. So I make this transformation you've seen before of z prime is exponential z. So if we look in the x direction, exponential minus x minus infinity is 0. So minus infinity goes to the origin. I've compressed 1/2 of the dimension to the origin. But exponential plus x plus infinity goes to infinity. I still have to worry about this one here. And then this y direction, exponential iy, goes to an angle here, a phase. And that's, as we go along here, we go around in angles. So I have this wedge or knife shape here. To get rid of the second half of the dimension, I do an inversion about this point. It can't coincide with the origin here, otherwise you'd unravel what you've done in compressing this dimension to the point. So I do an inversion about this point. So points near to the inversion point go far away. So this singularity goes to here, which is far away from the origin, which is here. Okay. And points at infinity go to the origin. So you've now got two singularities, and you've squeezed the x dimension here into these singularities. You've hidden that dimension here. But now I have a two-dimensional object. This is one-dimensional in this frame, and then the third dimension, the second dimension down here. So I want to re-expand it into a three-dimensional object with this fourth embedded dimension. And I do that with the usual log thing. Near the origin, log of the radius is minus infinity, and as I go around in angle I go up here, so I'm going through silver, and then as I go further out, eventually I bump into the interface between the silver and the dielectric, so I'm at this point here, and then as I go to a larger and larger radius, then I go out of the silver and here. And so what you've done is to take this three-dimensional structure and compress the dimensions into here, and you've hidden, and then you've expanded into another dimension and embedded them here. So you can calculate a dispersion relation to that, and it's perfectly ordinary. So this is the dispersion with a hidden dimension of the excitations, and at small k there's a big splitting, and as you go to larger and larger k, perfectly conventionally they converge on the surface plasma frequency. If you like fancy mathematical diagrams, this is a surface, dispersion surface of the hidden dimension along here and the non-hidden dimension along here. So you can actually draw a dispersion relation like that. I think more revealing is what the modes look like. So I start with the modes in the wave, in the slab frame, and these are just block waves, but it's a transformation that generates the structure. So as before, the singularity, the modes have a very, very high intensity. This is the log of the amplitude, so you get this huge intensity here because you get this compression as waves travel along this grating to this singular point. They slow down and they never reach the singularity because they think they're going into something like a black hole. It isn't a black hole, but it's a bit like it in that they go into it, but they never get there and they never come out. So you get this very, very rapid oscillation of the failures here. And that's what enables you to have a continuous spectrum, because since the waves never get beyond this point, it's as if they're traveling from plus infinity to minus infinity, and therefore the spectrum of this entity is a continuous one. So to conclude, emphasize the point that transformation optics is a design tool at the exact level of Maxwell's equation. It gives you an intuitive insight through the field lines that it works with of what's going on when you make the transformation, or what's likely to be a result of your transformation in terms of optics. And also, it relates the spectra of very diverse structures, and it can reveal hidden symmetries. And singular structures show local field enhancements that have a common origin in just planar waveguides, which go on to infinity. Similarly, we can relate singular structures to simple non-singular waveguides with an extra dimension, and this is a compacted dimension into the singularity, and they have a continuous spectrum, which is unusual for structures like that. And surface plasmonics is only one area of electromagnetism where transformation optics can be applied. So with that, I thank you for your attention.